Hello everyone, my name is Kishan Agarwal. Today I'm going to present my AAT TED Talk video of image processing, and my topic is convolutional neural networks for inverse problems in imaging. Introduction. Image restoration aims to recover a high quality image from degraded or incomplete data. Diverse inverse problems arises in imaging domains including photography, medical imaging, and satellite imaging. Traditionally, image restoration techniques such as sparsity-based methods face limitations in handling complex image structures and intricate details. So, in today, we are going to learn how to solve inverse problems in imaging using CNN, that is convolutional neural networks. It has recently been feasible to train deep CNN on large database of images, and they have shown outstanding performance on object classification and segmentation tasks. Motivated by these success, researchers have begun to apply CNN to resolve of inverse problems such as denoising, deconvolution, super resolution, and medical image reconstructions. And they have started to report improvements over state of art methods, including parity based techniques such as compressed sensing. So, convolutional neural networks have emerged as a powerful tool for solving inverse problem in imaging, demonstrating superior performance and adaptability. So CNN excels in extracting complex features from image data, enabling them to effectively restore, degrade, or incomplete images. So what are CNN? CNN are a type of artificial neural networks inspired by the human visual cortex. They consist of layers of neurons arranged in a hierarchical structure, with each layer performing a specific task. Key components of CNN includes convolutional layers, pooling layers, and activation function. So these different layers will help in the different tasks which we are going to achieve using CNN. So before that, what is inverse problem and contrasting the traditional approach to solve them with a learning based approach. So in the objective function approach, the reconstruction function itself regularized minimization problem, while in learning approach, the solution of the regularized minimization problem is a parametric function that can be used to solve inverse problem. So convolutional layers applies filters to extract local features from input images, capturing spatial information and patterns. Filters are learned during the training process, allowing CNNs to identify relevant features for the specific image restoration task. Next is, what are pooling layers? Pooling layer reduce the dimensionality of feature maps, making the CNN more computationally efficient. Common pooling methods include max pooling, average pooling, and sum pooling. Activation functions introduce non-linearity into the CNN, allowing it to learn complex decision boundaries and represent intricate the image patterns. Popular activation functions include sigmoid, tan, and ReLU, that is rectified linear unit. These are the different terms which we have used in convolutional neural networks. So using CNN as mean, roughly fixing the set of functions, sequence that is linear, filtering operation, altering with simpler nonlinear operations. So this class of functions is parameterized by the values of filters, which are also called as filter weights. And these filter weights are parameters over which the minimization occurs. So what are the applications of CNN for inverse problem in imaging? So image denoising, removing noise from image while preserving image details. CNNs can effectively learn noise patterns and filter them out while retaining the underlying image structure. So first application is image denoising. Next is image deblurring, that is restoring sharp image from blurred or motion blurred ones. And also CNNs can identify and remove blur artifacts, that is reconstructing the original image with improved clarity. So what is the approach? We know that neural networks are universal approximator. So more specifically, a full connected neural network with one hidden layer can approximate any continuous function arbitrarily well, provided that its hidden layer is large enough. The result does not directly apply to CNN because they are not fully connected. But if we consider the network patch by patch, we see that each input patch is mapped to the corresponding output patch by a fully connected network. Thus, we can call that CNNs are universally approximators for shift invariant functions. That means from the perspective of CNN work well because they generalize algorithms are vacuously true because CNN generalizes all shift invariant algorithms. On the other hand, the notion of universal approximation tells us that what network can learn, not what it does learn. And comparison to established algorithms can help guide understanding the CNN. More applications are image super resolution, that is enhancing the resolution of low resolution image to obtain high quality counterparts. CNN can learn upsampling strategies and generate high resolution images with more details and sharper edges. Medical image reconstruction, that is reconstructing high quality medical images from noisy or incomplete data. CNN can effectively handle noise in medical images and also can reconstruct detailed anatomical structures, aiding in diagnosis and treatment. So these were the applications. Now we'll see what are the advantages of CNNs. That is data-driven approach, end-to-end learning approach, and versatility. So what is data-driven approach? CNNs learn from large data sets. That means we need to provide large data sets as an input to CNN, then the different layers within the CNN will classify different functionalities which we want to apply on that image. That means large database sets of paid, degraded, and clean images, enabling them to capture complex image patterns and relationships. For example, if you want to identify object identification, you need to supply different data sets to the CNN model so that it understands the image patterns, and then it will able to detect the object. For example, if you are preparing the CNN model to identify a dog, you need to supply various images of dog as a data set to the input to CNN. That will make sure that it understand the image patterns as well as the relationships. And then if you give a input as a image of dog, it will say it is the image of dog. If not, it will return false. So this data-driven approach eliminates the need for handcraft features, that is making CNN more versatile and adaptable. Next is end-to-end learning. CNN can be trained directly from degraded images to clean images, eliminating the need for intermediate processing steps. This end-to-end learning paradigm simplifies the image restoration process and reduces the need for domain-specific expertise. Next is versatility. CNN can be applied to a wide range of inverse problems in imaging, demonstrating adaptability to diverse image restoration tasks. Their ability to learn from data to generalize new scenarios makes them valuable tool for various imaging applications. So these were the applications. Now we'll see what are the challenges and future directions for CNN. Interpretability. Understanding the internal mechanism of CNN and their decision-making process remains a challenge. We have discussed that we did not require a domain expertise to work as to run a CNN model, because all the layers which are intermediate layers in CNN will perform the task. So you did not require a domain expertise. But here, the understanding of internal mechanism, how that CNN works, remains a challenge for the user because he is not a domain expertise. Next is improving the interpretability of CNNs would enhance their reliability and allow for more informed decision making in image restoration tasks. This is the side effect of being the user, not a domain expertise, and using the product. Generalization. Ensuring that CNN trained on specific dataset can perform well on unseen data and diverse image restoration scenarios. Developing methods to improve the generalization capabilities of CNN would extend their applicability to a wider range of real-world imaging problems. So these were the challenges. More challenges: computational efficiency. Now, if we are supplying as a input large data sets, the time complexity, that means the training time will also increase. So this requires optimizing the CNN architecture as well as the algorithms, which may increase the computational efficiency and as well reduce the training time. This is particularly important for real world image restoration applications where fast processing crucial. That means, for example, in medical applications as well as in space applications, we require a very fast processing where the processing is crucial. So this is where computational efficiency is a future challenge. That means which can reduce the training time. So this was all about CNN. So computational neural networks have revolutionized the field of image restoration. by providing powerful and versatile approach to solving inverse problems by imaging, and now they are data driven. Thank you.